Okay, hey y'all, how's it going? My name is Anthony. I'm going to be talking about a really cool research paper called Bilateral Guided Radiance Field Processing. This is a paper I found from this year's CVPR conference, so CVPR 2024, coming from the Chinese University of Hong Kong by some really brilliant researchers, Rihao Wang, Chaoyi Wang, Bingcheng Gong, and Tianfeng Xue. Sorry if I messed up the names, but and they made some really good, cool, and performance gains in 3D reconstruction and towards this problem. So I'm gonna try to give a overview of this paper as well as dive into some details. But I'm gonna assume y'all have a pretty good understanding of the original neural radiance field paper. So the original NERF paper from 2020. If not, there's a lot of good YouTube videos and other resources on the internet explaining that. But let's jump into this paper. So a little bit of background though is when you take a picture, most modern cameras, it's like your smartphone and so forth, they apply a lot of post-processing after you click that shutter button. So this is called the image signaling processing pipeline, and it does everything from, on this picture on the left here, from white balancing, color interpolating, on a bunch of different things to get your final JPEG, your final image in your phone. Um, However, a lot of people, photographers and such, they actually shoot, raw images. So this is just inside the camera. This is just the light rays hitting that photosensitive film. No post-processing applied. Afterwards, though, the photographer may take that image, import it into a software like Adobe Lightroom, and add After Effects, um, bringing up colors, exposure adjustment, etc., whatever is part of their photography style. But about this paper though, bilateral guided radiance field processing, what does bilateral mean? Okay, so bilateral actually refers to a bilateral grid, and that's a data structure initially introduced to speed up bilateral filtering. So bilateral filtering is this image processing technique to remove noise. So on here I have some pictures. On the left, we have a noise image of the Taj Mahal, and a typical Gaussian blur can get rid of some of the noise, but you also lose some details in the building. So we can see lose a little bit of the edges and so forth. Bilateral filter, it does really good job of getting rid of noise while keeping those edges in detail. So this building looks a lot better. So it's a really powerful filter. But yeah, how does the bilateral grid work in this aspect? So likewise, like I said earlier, a bilateral filter is very similar to a Gaussian filter, aka Gaussian blur, Gaussian kernel, all the same thing, where each pixel in the resulting image after a bilateral filter is kind of like a weighted average of the pixels around it. However, Gaussian filter, the weight of a pixel depends on how far you are, particularly according to a Gaussian PDF. So if you're very far from a pixel, so here pixel P of image I, the formula is you sum over all their pixels Q to do this weighted average. You take the I of Q, which is the color at that pixel of image I, and you apply the weight of a Gaussian filter. So really quick overview, how a Gaussian blur filter works is just as the spatial distance between P and Q increases, this norm increases, right? This distance between the two pixels. And therefore the Gaussian PDF evaluated at a larger number is a smaller function value, aka smaller weight. A bilateral filter has this extra term where not only is spatial Gaussian, but there's this intensity Gaussian as well. So here, G of sigma R is this intensity Gaussian where it decreases the influence of pixels Q with an intensity value that's really different from pixel P. So if if you had two pixels right next to each other, they have a very low spatial difference, but if they're like on an edge, for example, they can have a very high intensity difference, right? So that could contribute to a lower weight in a bilateral filter. And in particular, this 1 over P in the front is just this normalization factor. So let's talk about, how does the grid exactly speed this up, right? So here on the right is like kind of a brute force implementation of how you would perform a bilateral filter. You just initialize, and for each pixel P, you're gonna initialize then loop through all the pixels Q and figure out the weighted average, right? You have to figure out the weight of each pixel Q, and then afterwards you can perform that normalization. So because there's two loops inside of each other, the complexity time here is S squared. So S is the spatial domain that refers to all the pixel coordinates. So the number of pixels, aka. You can restrict this inner loop value here. So instead of looping for every pixel Q and S, you can just loop through pixels that are distance less than 2 times sigma S. So 2 standard deviations away from the spatial Gaussian. You don't want to sample, you're not going to use that because already that's quite negligible. If you're outside 2 standard deviations, the weight is going to be pretty small. And this can lead to a faster complexity of S times sigma S squared. But this is still kind of inefficient for large spatial kernels. So exactly, the bilateral grid really, you can see the final complexity of a bilateral grid if you use it is linear in this size of S, as well as some other extra terms, and we'll talk about that. So what is exactly a bilateral grid, right? A bilateral grid you can think about as this vector valued grid where the input is a pixel, so a pixel coordinate, which includes a px and a py, pixel x, pixel y, and an intensity value. So those three things form the input. So it's a 3D grid, and it maps that to a 2D vector. Okay, this 2D vector here is explained right here is when you initialize it. It's going to be the 0 vector, or otherwise it's just going to be the intensity value of that pixel n1 if you're given the input intensity is equal to the actual image intensity. And then from therefore, the bilateral grid, you can to form a bilateral filter, you actually just do a Gaussian, apply Gaussian kernel. So for each point px, py, and r in the grid, you can consider a 3D neighborhood around that point. And then the 3D Gaussian kernel is applied to this neighborhood, and that weighted sum will be the output for this specific input. So how is this exactly faster, right? When you're here, let's just do a quick little runtime, a check. On step 1, this is just initialization of the bilateral grid. You just loop through every pixel. So this is where the size of S comes in. So the number of pixels. S is the spatial domain. Step 2 here is really the smart and clever thing with the bilateral grid is that when you convolve the grid with a 3D Gaussian, a 3D Gaussian convolution is separable. So you can actually break it down into 3 1D convolutions, and that's a lot faster than running a convolution between 2 3D objects. So along with this, the authors actually of the bilateral grid, the original authors introducing this data structure, downsampled the bilateral grid with a factor of sigma s along the 2 spatial dimensions and sigma r along the range dimension. So the downsample grid, when you downsample by those values, is the size of s times size of r divided by sigma s squared times sigma r, right? As you do that, where that in particular, so this is actually the size of the bilateral grid. When you perform 3 successive convolutions, the convolution runtime is dominated by the size of the grid because that's the largest thing. And so that's how this term comes to be. Finally, in step 3, you're just performing that normalization. So for each pixel, you're going to loop through all the pixels again. And that's just going to be this size of S again. So the number of pixels again. So really, really cool. Okay. Now, how does this all relate to the neural radiance fields and like 3D scenes and so forth? So the problem these authors address is that if you're given images from a modern smartphone, modern capture device like a smartphone, they want to create a more robust neural network against these ISP pipelines applied to the photos and use that to generate a much more accuracy, generate much more novel views, robust to these floaters from the post-processing, and also maybe perform some user guided enhancements. So now we'll see what that means and how the bilateral grid helps in that case. So quick note is like, okay, oh, yeah, here we go. Okay, why can't you just use a regular nerf, right? What happens if you use a regular nerf against images captured by a smartphone camera? So here I'm gonna play a couple videos. For example, here on the left is a bunch of input images we're gonna try to generate a scene of, and you can see like there's a lot of photometric variation in the brightness of the window. It's very bright, sometimes very dark in the shadows. Okay, if we just train a zip nerf on this on the right here, you can see we end up with a lot of floaters. And in particular, when this loads, yeah, there we go. When this loads, you can see like it's almost like there's like a white smoke cloud around this scene, which isn't the case. Just the network gets confused between the brights and the shadows, which is all the, what could be the white balancing exposure stuff that the smartphone camera is doing as post-processing. So that's an issue that this paper is going to address. And how does it exactly do that, right? In particular, so the authors first start off by assigning a bilateral grid, call it A, indexed by I, for each of the L training images. Okay, so AI, so this bilateral grid for a particular training image is a 4D tensor, dimensioned W by H by M by 12. Okay, so you can think of it as a 3D grid, but each grid cell has a length 12 vector. So I think this picture on the right here can help visualize it. Is you have the X and Y and the intensity. So X and Y are going to index into the W and H dimension. The intensity is going to index into the M dimension. And each of those grid cells in that grid is going to contain a length 12 vector, which represents a 3x4 color transformation. And say you had a pixel UV, right? And a color C. How do I, get a color transformation corresponding to those values? Is the authors define this like slicing operation, which is again this like weighted sum kind of interpolation formula. What they do is the weight is going to be this fancy K function, which they define below, which depends on this fancy lambda function, which they find further below, is this maximum. But that's the weight, and you plug in U, V, and G of C. So G in particular is this guidance function, which maps a color in RGB space to a scalar between 0 and 1. You plug that into the K function to get the weight, and the value for your weighted average here is just going to be the actual color transformation at the coordinates JK, IJK of the 3D grid of A. So yeah, to apply this bilateral grid to an image though, you basically, you loop through the pixels of that image, you obtain that pixel information, so its coordinates and its color, you slice into the grid using that information, get the color transformation, and apply that color transformation to the pixel. And you do that for all the pixels to get a bilateral grid rendered image. So how does that relate to the nerf? How does that fit into the nerf? The authors provide this really neat diagram here. And what I just talked about was this training part. So let's go through this. On the left here, after volume rendering a specific pixel, right? So they shoot a ray from the camera's position to the pixel of the image plane into the scene. After you volume render all the points along that ray, as you would do with a typical neuroradiance field, you take that, you do exactly what was aforementioned. You just take that pixel information, its coordinates and its color, slice into a bilateral grid, apply that to get the process color capital C subscript E, so CE here, and that will be your training output. So yeah, this computation graph here is completely differentiable. The gradients as you evaluate on the output can flow back very easily into this bilateral grid. So all the color transformations that were initially initialized as the identity color transformation will get updated to whatever color transformation that suits that particular training view. In practice, the authors actually also downsample this grid as well to hasten that runtime. So yeah, how do they train this exactly? So they introduce so as I mentioned, the gradients will flow back as is a differentiable process, but they also introduce some regularization. So they want this grid to behave a certain way. So I'm going to talk about this loss function that the authors use. L here is this total loss. So as you can see, this first term, as you loop over all the pixels, you take the typical nerf loss, which is just the square difference between the pixel difference between the pixels, and you square that. Sum of square differences between the pixels of the colors, which is the typical nerf. But here's the interesting part: is this lambda TV times LTV. So TV here stands for the total variation. So the authors in particular compute this new loss, which is this sum of weighted sum of finite differences. So here, L is the training index, so the training index view, and IJK, you're going to loop through the 3D grid cells. So IJK are what are we going to use to index into the grid. You compute the forward finite difference here, which is, if you haven't heard of finite difference before, it's just the difference between you and your neighbor in this grid cell. So you take a color transformation, you subtract it from your neighbor in the X direction, you do that in the Y direction, you do that in the Z direction. And you square those differences, and then you sum them up. So you can imagine, okay, what does this encourage is like, I want small finite differences. So between each grid cell, I want the differences to be small. What this encourages is a really smooth bilateral grid. And it's kind of crucial to the author's success that they really enforce a smooth bilateral grid. And in particular, smoothness matters because, first off, is for consistency. If you have abrupt changes in the color transformations of your grid, it can lead to like visible artifacts or, you know, inconsistencies, and as well as helping you generalize. So smoothness means like if you just move to another unseen viewpoint or slight variation in input, a smooth bilateral grid can help you generalize that faster. So along with that, there's better interpolation, right? A smoother grid just means slicing into it is much more smooth and easier, and overall more stable. So in general, there's this really big trade-off is when you smooth the grid, you may there's this trade-off between capturing fine details of an image, which require more, you know, abrupt color transformation changes between grid cells, and while there's this between the trade-off between that and maintaining overall consistency, which benefits from, you know, a smooth bilateral grid. So actually, they use a pretty big hyperparameter value of 10, saying that larger value was key. And I'll show some images the authors provided of some experiments they did with that. Okay, so without the bilateral grid, the NERF actually kind of learns an average appearance. What the bilateral grid does, the way they set it up through this training and regularization, is it has learned these view-dependent camera signal processing pipelines. So here in the second column B, when you render with the bilateral grid involved, remember the bilateral grid stores those color transformations. When you apply that to the rendered image here, you get much closer to the actual image in the dataset, which is this column C here. As you can see, the bright window is able to be brought out, whereas likewise with these dark shadows and so forth. So the authors try to answer a further question is, okay, what if you want to touch up the rendered image your own way? So the user has some interface to touch up an image and a scene as an entire scene actually in their own custom method. So let's say in this picture A here is just the rendering without the bilateral grid, and the user imports that image into some 2D view editing software. So this can be just like Adobe Photoshop, some Photoshop software like Lightroom. Then they bring out some colors. So here's some exposure is brought out, and the grass becomes orange, or so forth. What they do in C is they actually learn a 3D bilateral grid, approximate a 3D bilateral grid to approximate those changes you made in those touches up you made in Adobe Lightroom. What's really cool is they propose a method to generalize these edits from a single image to the entire scene. So here are novel views from different positions where the grass is still orange, and these edits are kept throughout the scene. So yeah, how do they do this? They actually, this is where the aforementioned picture comes in. They build another bilateral grid. So this time it's a 5D tensor or a 4D bilateral grid because the position argument you used to index into the bilateral grid was just a pixel coordinate, right? That position was a pixel x and a pixel y. Now you use an XYZ world coordinate as your position to slice into the grid, so this adds an extra dimension. Likewise, very similar to before, this slicing operation is just a weighted average. So the weight in particular is this fancy k function, which is just the previous k function with this added previous positionally dependent k function with this fancy new z term, and you pass in the color into that as well. And the weight is just your neighbor, so this as you're summing over all grid cells. Okay, so how do you actually, now that's how you slice into it, how do you get the pixel color for a particular view? When you have a particular view, your camera position, you shoot a ray into that pixel, right? And you go and you shoot that ray into the scene. Now, for each point along that ray, you're going to use, take that point's positional coordinates, query the network for a color, apply, plug the color in the position, world coordinate position, into this 5D bilateral grid through this slicing operation, obtain the color transformation at that 5D bilateral grid, apply to that world point, and you do that for every world point along the ray. Then you volume render that to obtain the final pixel color C for that view. And okay, so yeah, that's a very involved process, but this is if you have this H matrix, right? This 5D tensor, this 4D bilateral grid. How do you exactly learn that? So we do have, the information we do have is that original 3D bilateral grid, which we approximated, and that approximation tries to represent the user's touch-ups that they made in, for example, Adobe Lightroom. Now, to get the 4D bilateral grid, one idea is, okay, well, maybe we can learn it by just back projecting the values of the 3D grid. The authors, they'll come by a problem where actually only a small number of points in H will actually receive values, right? Because you go from a lower dimensional space to a higher dimensional space. So what they actually try to do is they try to reconstruct a low rank approximation of H. And they solve a rank minimization problem to kind of complete the matrix. Okay, so what does that mean? The formula you see here is kind of like a dyad summation, similar to other matrix decompositions like SVD. But this is, remember, this is a 5D tensor, so it's a little bit more involved. And these are outer products between these xi vectors. Okay, so when you take a outer product between two vectors, you get a rank 1 matrix, right? When you take an outer product between a matrix and a vector, you get a 3D tensor, and so forth and so forth. So that's why there's 5 vectors here. The specific decomposition here is a CP decomposition, which is a way to factor a high dimensional matrix into a sum of these outer products of vectors. So yeah, we don't know what the xi vectors are, right? But I'll talk about how you obtain those in a little bit, how the authors obtain these. So say you have them, you have these xi vectors. Here is a formula, is once you have them, you plug them into this new formula. So it's based on the fancy k function to define this fancy v function. You sum over neighboring v functions, concatenate them, and multiply it by matrix U to get the final color composition. So as you can see, this U is a 12 by R matrix, which is composed of the xi vectors, and together all of this creates the slicing operation. So okay, the big question is, how do you get these xi vectors to perform the slicing operation to begin with, right? It's not exactly stated, but the authors mention that they run CP decomposition on the 3D bilateral grid, because that's what they have. And then they also back project that, and then to get the xi vectors, so they run this decomposition, get the xi vectors of the 3D bilateral grid, and they use rank minimization to fill out the rest of the 4D grid. So the idea here is, once you back project some values of H, the values that you have, you ask the question, okay, what is the lowest rank matrix that matches the values I have currently? And this is, in general, this is a pretty interesting question because many data distributions in nature have a sort of low rank structure. And we'll talk about what rank they actually chose to fill out the matrix in a bit. I'll show some really cool studies the author did. along experimenting with this rank. But yeah, let's show some, when you combine all these steps, how does it actually do? So before, and this is with the zip nerf, you can see the floaters, but with the bilateral nerf, it's able to get much better results. And here the user, for example, touched up brought out some colors in the Lego bulldozer is more yellow, the mat is more purple. It looks much better. There are no floaters, and from the exposure differences and such. Some quantitative results here is like they have much higher PSNR values and other SSIM and LPIPs benchmark values that they received from affine aligning the sRGB space. So, okay, what does this affine align mean? Say you have some, and why do you do this? Why can you just not compare RGB values directly? Okay, so say you have some bias in your data set. So maybe like your all the images were a warmer tone, or too many warm tones, for example. The neural network, the original NERF, right, for example, will not only learn the views of the scene, but it will also learn the camera's bias to capture warm tones as well. So if you directly compare your rendered images from the NERF to the ground truth images, which are all warm, by the way, you kind of don't really know how well you've captured the scene, right? Just how well kind of it tells you how you've reproduced the camera's colors, the camera's bias to capture warm tones. So what you do is actually to affine align them is you take your rendered image and your ground truth image, you take a large number of corresponding pixels, and for each color channel you try to learn, you use like least squares regression, for example, to find a fine color transformation from the one set of pixels to the other. And where once you do this, you apply that affine color transformation for the entire image. It kind of helps you evaluate how well you capture the scene in its relative colors, because it's kind of like answering this kind of question. Like if your data set has warm tones and your rendered images also have warm tones, maybe your rendered image's tones weren't warm enough. I want to measure how well I've captured the scene. So I'm going to try to equalize this by making my tones just as warm by computing this color transformation. So making my tones just as warm as the ground truth images, so I can actually see how well I've captured the scene. So that's what the benchmark they use this. And this is actually mentioned in some previous papers as well. So such as like the MIPNERF 360 paper. Yeah, and you can see the floater removal in the depth maps. So with ZipNerf here, there's some floaters floating around above the couch, but the depth map of the bilateral guided neural radiance field is much smoother, much better. Yeah, okay, this is the what I'm trying to talk about earlier is with these studies they did with the rank and the hyperparameter, is you can see like, okay, if you don't add any total variation loss, so if you don't impose the bilateral grid to be smooth, the abrupt changes in the shadow really affect the render. It overprocesses it, and it results in these like kind of ghosts artifacts. As you increase the smoothing, you can see that it's able to counteract this. I guess in the bottom here, in the bottom here is what the experiments they did on rank. So, okay, like what is this lowest maybe rank 3 matrix to approximate that 3D bilateral grid to fill it out, the 4D bilateral grid, right? You can see as you increase the rank though, there is some strange blue color that emerges. So I guess what happens is maybe the model overfits, it gives into some color distortion, and compared to the low rank, which kind of maintains a more harmonized appearance. And yeah, here's some more results of how the retouching the scene. When you take an image from the raw MLP NERF, import that into Adobe Lightroom, approximate those retouch-ups you made in Adobe Lightroom with the 3D bilateral grid, lift that 3D bilateral grid into the 4D bilateral grid, you can generate really nice novel views of the scene with those effects applied. And that's pretty awesome how that happens. Yeah, this orange grass, appears orange and so forth. And, this green and more saturated appearance appears throughout. Yeah, and a really unique case is here the Lego bulldozer. They actually color it purple, and they are able to generate novel views of a purple bulldozer. Yeah, another cool case here is the environmental lighting. Around here in the scene, there's a different, the color changes, but with a bilateral nerf, it's able to be completely robust against that compared to this zip nerf baseline. Yeah, some limitations here is like, you can see in the top right, it cannot really handle transient objects. So for example, another paper, Nerf in the Wild from 2021 can handle transient objects, but just with a bilateral grid, it cannot, as this is not part of a camera's ISP. These clouds, as they move, they appear more ghostly, but they're sharper in their reference. And because you're only robust to the ISP, you cannot really handle huge changes in appearance, such as day and night, right? The authors do counter this by training, because it's a very modular data structure added to the processing part. They train a nerf with appearance embeddings, specifically the glow vectors. I'm not too sure how it works, but it's able to address this. So that's very cool that's kind of how modular this bilateral grid add-on is. And similarly, sharpening and blurring and coloring cannot necessarily be lifted to the entire scene. So you can see here in the top row is they sharpen the textures on that ground, but it's not able to sharpen in the finished render. Similarly, they recolor some of these window panes on this building, but the exact coloring cannot be matched. It's very difficult. Yeah, overall, it's a really incredible. This paper is able to achieve some really great quality results. So here, this first chart on some different data sets, the red in particular represents doing the best, and without a fine alignment, it actually does the best on average. When you fine align it, the PSNR score not only jumps a lot, but it still stays in first. So it's as well as just great renders, it's the ability to edit an entire scene just by only editing one picture, right, in Adobe Lightroom is very, very cool as well. But yeah, that's all I found from reading this paper. I hope you guys enjoyed this really cool paper and this kind of talk through about it. Yeah, thank you for watching.